Hello, Year 12. By now, we've completed the test on force and momentum. And the next part of the course is we're moving on to Chapter 10, which is all about energy, well, call it work, energy, and power. And you'll find it on page 148 in your book. That's the old book, by the way. And no idea what it's going to be in the new book. You can look it up yourself. Work, energy, and power. And we're going through the 10.1. And in 10.1, you've got to state different stores of energy and transfer mechanisms, state the principle of conservation of energy, and then state relationship between energy transferred and work done, and state the significance of the area under a force displacement graph. Now, the first part of this is what is the principle of conservation of energy? And this, to be perfectly honest, is the most important law in physics. It has never been broken. And basically, the law of conservation of energy says energy cannot be created or destroyed, or it can be basically is transferred from one store to another store. In other words, all the way back to the Big Bang, the beginning of time, there was a certain amount of energy there, and this energy has been spread about the whole universe, slowly but surely. In fact, the universe is cooling down. And yeah, it's true. And when you get down to it, a lot of the laws in law of physics all comes back down to conservation of energy. Never, ever has been disproved. And we did usually look this way back in GCSE. Very, very important law. And we can use it over and over again. And later on this course, we look at kinetic energy, etc. We always look at the fact that energy must be conserved. It's got to go somewhere. Going at that, now this is a problem. And the problem is this was introduced at GCSE, and it was introduced a couple of years ago. Now, some of you will be taught basically forms of energy. In your book, it talks about forms of energy. We have yet to see a proper GCSE question on this. Some of you now will start being taught about stores of energy, and you should be familiar with this, but we have yet to see exam questions on it. So, the book is different to the book, and we've yet to see it's really because they've done it at GCSE first rather than A-level, and the A-level books never caught up with it. But we now need to use terminology of stores rather than using forms of energy. In other words, you can start off with a store of energy, and it can be transferred to other stores of energies. And the stores they deal with are chemical, gravity, kinetic, thermal, elastic, vibration, nuclear, and electromagnetic. This one I've started to see sometimes as called magnetic energy. And if you're looking at that straight away, and you'll see this written down in your book, there are some missing. If you look at it and think about it, what is missing? Well, there's no light, is there? There's no sound. And the argument now is that light and sound are not stores of energy. Light is basically where energy is transferred from a light bulb or the computer screen you're staring into now into your eye. Therefore, it's a way of transferring energy. There's no electrical store of energy. Electric current is all about transferring energy from a chemical store from a battery, but it probably ends up the light bulb and it ends up coming out as thermal. So we don't expect questions on this, but you should be aware of it. To show you this in an example is these stores can be transferred by the 4 different mechanisms. Heating by particles, what I'm on about conduction. Heating by radiation, also this one as well, you can argue convection comes in there. Heating by radiation is all the idea of light. And therefore, if you're staring at the screen now, you've got energy being transferred from the computer screen, like I said before, into your eye. It's still about heating by radiation. That's light and infrared. Electrical working. This is all the idea of a cell. When you've got a cell, you've got a chemical store, and then eventually it could end up to being an electric motor. And then it goes into kinetic energy store. Mechanical working, that is all pushing, pulling, that is all friction. For example, if you've got sliding a book along a bench, etc., you are taking your chemical store and you're pushing it along, and the bench is going to a kinetic energy store because it's moving by mechanical working. To show you examples, and these are tricky, but I did start doing these GCSE, is like a ball falling downwards. Now, to get these right, again, I don't think any exam questions on them, but I'm trying to make sure you understand what the energy stores are all about. Is if you've got a ball and you're letting the ball fall down, you've got to get your start point, end point correct. If you don't get the start point, end point correct, the whole thing goes pear-shaped. So therefore, my start point is the ball is going to be at this height here. The end point is going to be the ball just before it hits the floor, and here's going to be a floor just here. So we've not hit the floor, we're just about to hit the floor. So what we say then is we are starting off with a gravitational store at the top here. Then as it goes down, this gravitational store becomes less and less, and then we go into our kinetic energy store. But it does this by mechanical working because the force involved in this, therefore this store goes to that store. Getting it? Next one. This one could be based through a nice big torch here. Now the start point, the bulb is on. Very excitingly, 5 minutes later, the bulb is still on. Now, what are we on about here? Well, first of all, you got inside here your batteries. Therefore, you start off your chemical store. Then, 5 minutes later, because the light is on and you can't say you've got a light store, you're then going to get a thermal store because you're basically heating up the air around here, aren't you? Therefore, it does this because you've got your wires going in here, connecting the cell to the bulb. The bulb can be just here. It does it by electrical working. Then eventually the bulb is going to light up. And then what we say is then it's going to warm up the air on the outside by two processes, by heating by radiation, which is like the infrared, like I mentioned before, and also because you've got the heat up the particles, you've got heating by particles as well. I won't get bogged down, or you shouldn't get bogged down by these. They are tricky. We don't expect exam questions on them, but we are now moving away from forms of energy to stores of energy. So, what is meant by work? Well, you should know all the way from GCSE what you've done is this equation here. Work done is equal to force times distance, and you've got that in your book. Okay? Now, this one you've learned, you know then work done is basically force is measured in newtons and distance is measured in meters. Therefore, work done is Newton meters. But also it is measured in joules. This because what we mean by work is when you apply a force, and say example could be a block or whatever it is, if you apply a force F, it's then going to move a distance delta S or S. Okay? So sometimes you'll see, and I'm sure the way your book does it, it doesn't. Sometimes I've seen an equation written down F delta S, where delta S is going to be a change in the distance. You are basically making this object move. What you're doing is you're doing work. Therefore, you are transferring energy. For example, if you take these blocks here, and this nice young girl's lifting the blocks going up to higher up here, she is doing work. She's going to get tired doing this eventually. Therefore, she's doing work while she's applying force against gravity. She's then lifting the blocks at this height, 1 meters. Therefore, work is simply meant is when you're transferring energy, you're applying a force over a certain distance. And you should be familiar with that with the work you did at GCSE. Now, the important thing is now these must be in the same direction. In other words, the force is going that way, and the delta S, the direction is that way, and they must be in the same direction. And this will come back big time in year 13. We look at gravitational and we look at electric fields. The force and distance must be in the same direction. Hence, look at this situation here. Now, any sailors are here, you know about tacking, where you've got your great big wind blowing here, but you don't always want to go in the same direction as the wind. Sometimes you want to go in the opposite direction, a slightly different direction. So here you've got a lovely boat. Using the sails, the force of the wind is going that way, but you're making the boat move this way. Now, I'm going to say now the angle between the direction the boat's going to move is theta, and the direction of force is going to be F. Now, we've written down the equation that work done is going to be force multiplied by the distance, and this is going to be a delta S going through here. Okay? We can see now they're not in the same direction. What you've done before in year 12 gives you the equation, because won't it be now it was going to be your delta S cos theta. And the reason why it's going to be cos theta is because, again, you're going to crush the angle. I'm looking at the component of delta S in here. Therefore, this can take it into vertical and horizontal components. Therefore, I take this one now, the delta S going that way, it's going to be delta S cos theta. And you met that quite a few times. This is a new equation now, step up to year 12. And you should be happy with it. Also, in this little chapter, first got to get you going, is you can have force distance graphs. Now, again, we know the equation, and now I'm write it as straightforward F, because F delta S, and you really think about it here. If you're going to move distance S from here to there, if I do F multiplied by S, isn't it going to be the area under the graph? And you keep meeting this a lot of the times. Work done equals force times distance. That's nothing new to you. And yeah, simply the area in the graph. Therefore, what the heck are you going to do when it comes down to this? Well, if you now got a force that's varying with time, it's not constant. Again, what we do is we take a little strip like this. We say that is going to be delta S. Therefore, the work done for this little bit here is going to be F delta S. And what you do, again, it's no different to what we've done before, is to work out the total work done is going to be the area underneath the graph. Now, as I mentioned a few times when we're teaching you, there's a process called integration. And integration, you get the equation off of the line and you basically integrate to the limits from here to here. But hey ho, at A level, they don't do integration. Well, they do it in maths, but they don't do it in the physics. Therefore, to work out the total work done, I'm afraid you have to count squares. So it comes into good old counting squares process, which we all love. And it does a headset, doesn't it? There you go. Therefore, you get a grid going here. You've got squares. And what you do is you work out the area of one square by using F multiplied by S. And then you count your squares up. And to recap links to this, beforehand, where you had a force extension, graph of good old springs. Remember, you put a mass in a spring and the spring went down. You had force extension graph. Well, in this case here, remember we called the extension was going to be delta L now. And we then said the work done this one, and you'll find this all on your page 150, is go from there. You can find then the work done is the equation going to be F delta S. And this time now, the work done is going to be a half F delta L, because again, it's going to be the area under the graph. But to remind you, is we then had force equals K delta L. And you can remember K was going to be the spring constant, therefore isn't the work done now going to be a half K L delta L squared. And that equation links back what we've done before. Okay, hope you enjoyed the video. I'll leave you now to get cracking on to the summary questions on page 150.